by the strong force in nuclei. Oxygen-16 contains...
That clip was from MIT, Visualizing the Nucleus on YouTube. That is not correct, and we've known that for 75 years. Maria Mayer developed the theory of nuclear shells. Protons and neutrons do not reside in the same nuclear shells. And she discovered this 75 years ago. Let me show you what the nucleus actually looks like. Let's take lithium-6, for example. This is what conventional physics tells us the lithium-6 nucleus is. These are the neutrons and these are the protons. And they show it to us as a cluster of grapes. That is not what the nucleus looks like. Neutrons and protons are in different nuclear shells. You have to think of them like little droplets of water. When two neutrons get close enough together under the right conditions, they merge and they form a single ball, a single nuclear shell. Three of them forms one big ball with 2 down quarks and 1 up quark for each one of these. So you'd have 2, 4, 6 down quarks and 1, 2, 3 up quarks to form the neutron shell. With the proton shell, you've got 2 up quarks and 1 down quark in each of the protons. So you'd have 2, 4, 6 up quarks and 1, 2, 3 down quarks. All those have to form together in the new droplet when they merge into one nuclear shell. In the case of lithium-6, the protons take the outer shell, so you'll have one shell, one sphere of protons on the outer shell, and you'll have a sphere of neutrons on the inner shell. This is the structure of lithium-6. Now what you see are a couple of strings pinned to it. The nucleus itself is made of hadron string, but these strings that pin to it are a condition of the geometry. This is a p-orbital. Usually you'll have an electron stuck to that, and if it's covalently bonded to another atom, you'll have 2 electrons, one on either side of the string. This string could pin to the other nucleus, or it could just float free like this. You don't always need a p-orbital like this in order to form a covalent bond. You could, if there are no pin vector bosons, then the electrons, each electron has a lepton string pinned to it, like a little loop pinned to the side of it. And when you put 2 electrons together, you form a Cooper pair. And you'll have 1 electron on either side of a loop of string. And they will float between the nuclei, and their charge basically holds them together like that. The p-orbital usually forms from the top surface, but in this case, lithium, there are not 2 quarks sandwiching that lower orbital, so it takes the p configuration, the negative charge wind blowing off from that down quark, pushes on the lepton string and forms it into that teardrop-shaped lobe. Here, if we can see it a little closer, you've got a string. The pin vector boson is stuck to the quark on the lower nuclear shell, and there's an up quark immediately above it on the proton shell, on the outer nuclear shell. And it can't form into that teardrop lobe. It's basically squashed in there, so it gets hybridized or linearized. And you get this big loop instead. Now that big loop, it'll also have an electron or 2 electrons attached to it. It doesn't have to. There are some nuclei where there aren't enough electrons to go around. Some of these strings just hang out in space by themselves. But the linearized orbitals or the hybridized orbitals are very important for metals. Here are some examples of some different bonding configurations. Here we have a p-orbital with 2 electrons bonding these 2 nuclei together. You can see the string is not pinned on this nucleus. Here we've got the string pinned to each of the nuclei with the 2 electrons in between, and with no lepton strings pinned, you'll get 2 electrons on a little loop of string floating in between them, between the nuclei. Here's an example of a linearized orbital that you'll find in metals. Instead of 2 electrons joining them, 1 interstitial electron forms between each of them, and that frees up more electrons into the conduction band. So that's why metals conduct electricity. They're not using all their electrons. The extra electrons aren't pinned. They're floating freely through the metallic conductor. So when you apply electric current to it, they just move from nuclei to nuclei. Just a quick view of that. So if I apply a current to a metal, the free electrons, each one of these is an electron with a little loop of string, the pin vector boson, that's a lepton string. They'll float freely in the conduction band. If I apply a current, these will move along, whereas these will stay pinned between the nuclei. In a superconductor, we get a different situation where 2 electrons pin together. They're at low enough energy and low enough noise that they will pin together on a finite loop of lepton string, and they will move in pairs through the conductor, or through the superconductor rather. Excuse my mess. Here's another example. This is a polar view of the boron-10 nucleus. You'll see on boron-10 there is 1 hybridized orbital, that big round one at the bottom, and there are 2 p-orbitals. Like I say, pardon my clutter. Being ADD and untreated makes for a messy home. Anyway, what you'll see on this one is every down quark is above an up quark on the lower shell, and every up quark is above a down quark. So what you're seeing here is the charged surfaces of the quarks are attracted to each other because you have positive and negative. This is what constitutes the strong nuclear force in the nucleus. It's these charged surfaces being so close together. Now here they're shown apart. These models are very hard to build stacked like this. So most of my shell models are just the individual shells. But I took the time to do lithium and boron-10. Boron took me 12 years to solve, so it was kind of the holy grail of physics for me, because boron's a semiconductor rather, and I wanted to understand semiconducting properties. Well, semiconducting properties are largely because of this hybridized orbital that can do the metallic bonding configurations. Whereas these p-orbitals, they do standard covalent bonds and such. But as you see, this is a very tightly bound nucleus with its proton shell and neutron shell, every quark having a complement on the other nuclear surface, and they're all aligned with each other, so they stick together very, very strongly. That is your strong nuclear force. Every one of these strings is a string of corpuscles of light. The nucleus is made of hadron string, which is a different kind of light than these. These are lepton strings. Electrons are made of lepton string. Now, they say electrons have no structure. I argue with that, because what we're looking at here is hadron strings form in hadron space, and lepton strings form in lepton space. Now, what you do, or how you can understand this, is you take the 3 dimensions. Both types of strings share a common time-like dimension, but if you take the 3 dimensions of hadron space and make an orthogonal rotation, like a 90-degree rotation in all those strings, and reassemble the 3 dimensions, then what you see of the electron is not its structure. You see a cross-section of where those strings intersect in hadron space. So it appears to be a point particle, but it's really not. It actually does have a structure in lepton space. We just can't see it because everything's turned at right angles. So all we see are points where the electron intersects with hadron space. And that usually occurs with the down quarks, because down quarks, they're kind of tricky. The up quarks have two mirror surfaces, but they're both positive charge mirrors. The down quarks have two different charge mirrors. A down quark is minus 1/3 charge, and an up quark is plus 2/3 charge. And with a down quark, you've got a positive and a negative charge surface. The negative surface is larger than the positive surface. So basically you get a minus 1/3 charge for the down quark, and you get a plus 2/3 charge for the up quark. But it's enough to stick them together because you got negative charges and positive charges close together. That gives you your strong force. So that was for the boys at MIT. So now you know what the nucleus actually looks like. You can find more information at my website at stringtheory.com. It's been up for over 20 years. Physicists tend to ignore it. A few go in to steal ideas from it. You know, physicists have been stealing from my work for a long time, especially my cosmological work. Now, I finally got tired of it. It was a waste of time for me to pursue physics because physicists wouldn't give me any acknowledgement whatsoever. So I turned my interest to other things.